So we're given the first derivative of a function, asked to find the local max and min, the intervals of increase and decrease, and we're supposed to sketch a possible graph of the original function. First, you can notice that f prime is a polynomial, so f itself is a polynomial, so we'll just keep that in mind when wondering what this function looks like. Also notice that our first derivative is given to us in a factored form, which is great, because we want to find the critical points of our function, and we find critical points of a function by setting its derivative equal to 0 or asking where the first derivative does not exist. And since this first derivative exists everywhere, we'll just set it equal to 0. And solving an equation that's factored and set equal to 0 is fairly straightforward. We set x minus 1 equal to 0, and that gives us a critical point of x equals 1. The second term then gives us a critical point of x equals negative 2, and the third term gives us a critical point of x equals negative 5. Okay, so we have 3 critical points. Let's draw our number line. The number line doesn't have to be pretty, it just has to split up our domain into pieces, and in this case, since we have 3 critical points, we're splitting our domain up into 4 pieces. And on each one of these 4 intervals, our original function is going to be either always increasing or always decreasing. So what I'm going to do is choose a single test point from each one of these 4 regions. And we're going to plug it into the first derivative of our function to see whether that first derivative is positive or negative at each one of those test points. I'm going to make a little bit of room for this work. Let's start by plugging in our test point of x equals negative 6 into our first derivative. Doing that gives us negative 7 times negative 4 times negative 1. Now the answer is negative 28, and what's important about that is whether it's positive or negative. In this case, our first derivative is negative at the point x equals negative 6, so that means that our function is decreasing on the entire interval from negative infinity to negative 5. Now for the rest of these test points, I'm going to kind of just speed through the work. When we plug x equals negative 3 into our first derivative, we get a positive result, meaning that our function is increasing on this entire interval. When we plug x equals 0 into our first derivative, we get a negative result, meaning that our function is decreasing on that entire interval. And when we plug x equals 2 into our first derivative, we get a positive result, meaning that our function is increasing on this interval. Okay, now I'm going to enlarge the results that we just got from our number line right here, because I think that this graph is pretty telling. We can see that our function is going down on the interval negative infinity to negative 5, and then the function starts going back up on the interval from negative 5 to negative 2. What that means is we have a local minimum at x equals negative 5. We can use that same logic to argue that we have a local maximum at x equals negative 2, and to argue that we have another local minimum at x equals 1. Just so we answer all of the questions, we know from this graph that our function is increasing on the interval from negative 5 to negative 2, and on the interval from 1 to infinity. We also know that our function is decreasing on the interval from negative infinity to negative 5, and on the interval from negative 2 to 1. As far as a quick sketch of what this function might look like, we can try to put all this information together. We have our 3 critical points at negative 5, negative 2, and 1. Our function decreases until it gets to x equals negative 5, and then it starts to increase until it gets to x equals negative 2. It decreases again until it gets to x equals 1, and then increases all the way off to infinity. Now, if you're sitting there saying that's not the sketch I would have drawn, well, that's okay, because it's not the only possible sketch. Another sketch would be something like this. There we go. The only similarities that they have to have is that they have to be increasing and decreasing on the appropriate intervals, and they have to be as beautiful as my sketches. So okay, I guess that is it. I'm going to see if I can zoom out on this and show you all of the work in one screen. Cool, so I hope that helps you out, and I hope to see you next time for the calculus problem of the day.